All right, you're good.
Okay, everyone, my name is Dr. Shelton Gay. I'm with the Science Center. I've been working in the physical oceanography of Prince William Sound, and particularly its fjord systems, for about the past 25 years. And this particular program is on Port Valdez, which is one of our larger fjords located in the north central Sound. I'll give you a little bit of background on the study. Okay, this study was originally suggested to RCAC by Scott Pagao here in 2015, and I was consulted to lead the project. I submitted a proposed study plan in August of the same year, and funding was approved in September for fiscal year 2016 and 17. Minimal past circulation studies, including those of UAF and IMS environmental impact work in the early 70s and 80s, were done. And Minchin Hagee in 1978 and Joseph Colonel in 1981 also wrote papers on deep water exchange for PWS water to Port Valdez. But other than that, there's not a lot that had been done. So this project had goals to measure currents and circulation using hydrography and towed ADCP and drifters at 4 depths. And we wanted to determine the important forcing mechanisms and observe how these vary seasonally. So the primary end uses of the data involve validations of circulation oil spill trajectory models, but other uses include developing specific contingency plans to address scenarios based on where oil may go and to determine areas requiring more protection. Also, under what conditions, based on the seasonal circulation, should dispersants be applied. So Port Valdez is located in the north central part of the Sound, and it's tucked away inside the Chugach Mountains, which surround it on all sides. And the port is 18 kilometers in length, which is about 11 miles, and it averages about 5 kilometers or 3 miles in width. It's shaped like a bathtub. It has a smooth bottom with maximum depth of 240 meters or 790 feet. The ancillary weather and tidal data were provided by the NOAA Seaman Station, and that's shown here, the red star. It's located next to the Alaska Marine Highway Terminal. Okay, like Prince William Sound, the sources of freshwater input are scattered around the periphery of the whole fjord, so you can see all these streams, but the largest sources occur from the Low and Rogue rivers in the southeast, and additional sources occur around the northern side from the Valdez Glacier Stream, here to Mineral Creek, Gold Creek, and the Shoup River. So there are 3 seasonal experiments that were performed in late June, September, and March. And each of these periods had an associated set of weather and oceanographic conditions, and I'll be describing those individually in a lot more detail, but you can see from here that the summer pattern was warm with daily sea breezes, and the early fall was cool and wet, and we had variable winds, and it was a start of the surface cooling and period of maximum freshwater input. Late winter went from cold, dry conditions with strong easterly winds, but then the winds abated, and we had some warming and snow and periods of calm, lighter westerly winds. Okay, the oceanographic instruments that were used consisted of hydrography data collected with a CTD and currents measured by a towed acoustic Doppler current profiler, or ADCP. Now, the CTD stands for conductivity, temperature, and depth, and the data are used to obtain profiles of temperature and salinity at 1 meter depth intervals based on a pressure sensor. Those 3 variables are then used in the equation of state to calculate water density in kilograms per cubic meter. And that's an important parameter to look at the geostrophic circulations, which I'm going to describe also in more detail. The horizontal variations in the density field then are used to compute that dynamic topography and the geostrophic flows. The ADCP measures currents by sending out sound pulses, and this one's 150 kilohertz, and sends them sequentially from 4 transducers, then listens for the returning echoes over specified depth intervals or bends. The echoes have a Doppler shift associated with both the water and the boat motion, and the instrument separates the 2 by removing the vessel's velocity. Now that's determined by bottom tracking to get the speed over ground and the directions obtained by an internal compass. 3 of the transducers measure the motions in the X, Y, and Z axes, and the 4th beam is used for redundancy to obtain a measure of data quality called error velocity. And those parameters, including percent of good returns, are used for evaluating data quality. So in all months, the transects have the same pattern, the ADCP data, but in the interest of time to make enough ADCP runs, the CTD station layout was changed in September and March. So, whoops. So, for example, in June, the stations were set to provide more long channel resolution, but the number was increased in the fall and late winter to 4 in the cross channel direction over 3 transects number 1, 5, and 9. The total transect runs in June were 16 and transects in 6 runs of stations, and in September these were 14 and 8, but only 5.5 and 3 sets were performed in March, and that was due to the harsh weather that we encountered. Okay, the surface drifters are called I-spheres or oil tracking buoys. There's a picture of these guys here. And they have about half the hull above the water surface, so they are directly affected by surface wind stress, and that moves them at about 3 to 5% the wind speed. For example, a 10 knot or 5 meter per second wind could cause an additional motion of about 15 to 25 centimeters a second. They are also affected by wave action and surface currents, and as such, they have the greatest tendency to ground on shore, become stranded during high tides. Also, because of their marked tendency to become grounded, fewer of the I-spheres were typically deployed in comparison to the microstars. So the microstars are designed to track currents near the surface, and the drogues cover a depth range of 0.5 to 1.5 meter, which happens to be the same as the first depth bin of the CTD data. So the center of the drogue is at 1 meter, and they have a drag ratio of 40 to 1, so there's negligible effect of wind stress and surface currents on the surface buoy. When the wind speeds were low, these drifters moved nearly as fast as the I-spheres at approximately 20 centimeters a second, which is only 0.4 knots. But under moderate to strong winds, they moved at about half the speed of the I-spheres. Now, they could be affected by wave action, but they have a limited tendency to ground on shore in comparison to the surface drifters. So the last group of drifters that were deployed were the Surface Velocity Program Drifters, or SVPs, and they have a wholly sock drogue shown in the upper left picture here. The drogues are centered at 10 and 40 meters, and they're designed to measure subsurface currents caused by various responses to surface transport by winds, tides, and subsurface variations in water density, and all these factors may interact to create subsurface barochromic modes of flow. The motions of these drifters were slow, typically 5 to 10 centimeters a second for the 10 meter drifters, and about less than equal to 5 centimeters a second for the 40 meter drifters. And due to the slow drift speeds and hence longer drift periods, fewer redeployments were made for these buoys. For example, the 40 meter drifter released in June remained in the water for nearly 6 days. So when you put it in, it stayed in to the end of the study. Now the deployments were made and retrievals made initially from the Auklet, but then at the end of the oceanography period, we used the high-speed vessel, the MV Vixen. So occasionally this involved tracking down drifters southward into Valdez Arm, and there were also some times when wave conditions prohibited use of the Auklet skiff, or the drifters were too far away from any of the transects, and in those cases the Vixen was used in to retrieve and redeploy buoys. Now, the number deployed each month was shown in this table, and in June, well, we had to be a bit conservative at first due to political concerns regarding potential conflicts with shipping. But we knew no problems would arise. When we knew no problems would arise, the buoys were released in groups. In September, the drifters were released in groups right away, and due to more rapid drift times, there were more redeployments made. So the total was more than 1.5 times those in June. So I had 93 versus 56 total drifters deployed. In March, the numbers were again low due to the initial problems of weather. We didn't get out until about the 24th of March to actually deploy the drifters. But after that, we did get a lot of repeated drifter deployments made in groups. And so we ended up with a total number of deployments that was less than in June, but the numbers of drifters deployed were the same. So I'm going to start with the summer results here. And starting with the winds, over the entire month of June and during the survey period, which is shown in blue up here, the wind patterns were dominated by daily diurnal westerly sea breezes, and the predominant westerly directions during the survey are shown in this wind rose pattern. So all the histograms showing westerly to southwesterly winds, and these are all the wind vectors during the entire survey. So you can see the daily westerly to southwesterly winds blowing in, and at night the winds would relax, and then sometimes they blow southward. We're from the northeast, and so we blow down the fjord, but it was a fairly light set of winds. And then the next diurnal period wind would start around noon the next day. Okay, these are examples of the hydrography data collected in June, and therefore this first set of this first transect here in the inner basin, right up here. So the PV-17 is the station located down in the southeast corner, and then 14 is up here in the northeast corner. But you can see in the upper 5 meters or so, there's effects of cold runoff, and this overlies the seasonal thermocline, where earlier solar heating has been occurring over the spring to early summer. This deep inflection area here is a temperature minimum that's a remnant of winter cooling, but below that, the temperatures are all relatively uniform. The halicline in June is very, very shallow. It's very steep here, as you can see. It's within the upper 5 meters or so. And below that, the salinity just gradually increases down to a depth of about 60 meters, and beneath that, it's pretty homogeneous. So this is a temperature versus salinity diagram. And I'm showing this because I wanted to emphasize the role of salinity in affecting density. These contours and the dotted lines, those are all contours of sigma T. And sigma T is the density of the salt water, but with fresh water removed. So it's with 1,000 kilograms per cubic meter removed. So what's left is density based on the dissolved salts. So this shows that the water in the inner fjord, on the very, very last CTD run, which is F, is colder and fresher, this water right here, in comparison to the outer fjord, which is warmer and more brackish. And you can see that there's a density difference between those two. And it's not huge, but it's enough to drive some flows. So let's look at the temperature structure over this set of this transect right here going along the northern side over all the CTD runs. And this goes from PV-14 in the inner basin and ends with PV-1 out here in the outer basin. So the spatial structure of the temperature on run A shows the effects of the cold surface runoff in the inner basin and this thick warm water out here in the mid-basin. But the changes over time in the structure of temperature indicates that the water is being advected inward by the westerly winds during the afternoons. So here you can see in B this water being moved in, and then at night the water moves back down fjord on this northern side. So on C we see the cold water moving back out. Again on D, this warmer water has moved back in, and in E, it's moved out again, but notice that this brackish warmer water, which is denser, is actually underriding the surface water. So what you get is an oscillatory pattern in this hydrography, and that shows up in the salinity as well. So if we look at the salinity structure, we're going to see the horizontal gradients between the inner basin and the outer basin. And here's that thick layer of brackish, warmer water. What happens on the westerly winds, it moves in, and then at night it disperses back out. And then during the next set of westerly winds, it moves back into the basin, and then moves out again during the night. So here we have in the last run, the westerly winds actually are bringing it up into this area right in here. It's concentrated up in this area. But we can see this a lot better if we look at the dynamic topography based on CTDs. Okay, this particular slide is going to take some explanation. These are dynamic heights based on the CTD data. And what we do is we calculate them by taking this density distribution and using the inverse of that, the specific volume anomaly, and looking at its distribution. And now that's in meters cubed per kilogram. So once we have that, and that anomaly is determined by subtracting the standard density with a salinity of 35, temperature of 0 Celsius, and at each pressure level. But before the SVAs can be used to compare or to determine currents, they have to be converted to geopotential heights. And that's done by integrating the SVAs over pressure, i.e. that's multiplying each SVA by the pressure in pascals or newtons per square meter. So the geopotentials are then expressed as meters squared per second squared, and that's the same as energy in joules per kilogram. And the currents are found by taking that and dividing by, you take a difference, let's say, between two stations, say up here, these two stations, and you take the difference in that geopotential height, and you divide by the Coriolis parameter, radians per second, and then the distance between them, you end up with meters per second. Now, I know that's a lot of explanation, but it's how we go from the density field to actually getting a set of geostrophic currents, because they're a relative velocity based on a level at the base of no motion, where you have to assume there's a level of no motion, so that when you integrate through the pressure, that's the point of zero flow. So these currents are not always going to be that accurate, because you can't always assume that there's no motion down there, but it's not going to be off by a tremendous amount. It's not, because the deeper currents are definitely not that strong to begin with. We'll see that in the ADCP data. So anyway, the structure of the density field changes. At the start of the westerly winds right here in A, we're seeing dispersals, the stuff starting to move in, but at night on B here, it's already in the inner fjord and we're starting to get a gradient moving back out. Now on C, at the beginning of the next set of westerly winds, the same setup is here, the dynamic height. So we're going to start to see a motion back into the fjord. At D, we're in the middle of those westerly winds, you can see the water's been moved into the inner basin and concentrated along the northern side of the fjord. So this is constantly putting the currents in a state of flux, and it's due to the interaction of the winds, tides, and changes in the freshwater distribution. And this is seen in the restructuring of these higher specific volume anomalies over the inner basin when the winds relax at night, and then reverse structure again when the winds pick up the next day.
So is Shoup Glacier your primary source of fresh water then?
No, because it's out way in the western side of the basin.
Right, but your minimum salinities out to the west. Your dynamic heights are out to the west.
They reverse each other. I don't have any data out there by the Shoup. We're right at about mid basin where the CTD's end.
Yeah.
So that's a good question, Scott, because I really don't know how much influence that Shoup has, but I would suspect that if it does, it primarily influences down through the Narrows area.
If it's blowing from the west.
I don't know why it would do that, because I mean, if it's coming out of that area of Coriolis, we want to make it turn down to
but if it's blowing from the west, it's going to push it in.
It could send some of that in. So yeah, it's a possibility that it's one source. It's never been mentioned in any of the environmental studies as being the major source of fresh water, though.
Okay. We normally measure fresh water coming off of the glacier.
Oh, they had in the environmental studies done by UAF, they did have some measurements of how much freshwater input was coming from these different sources. But anyway, let me continue here. It's the so this is the surface ice-sphere trajectories from the June 22nd to the 27th, and it shows examples of 3 ice-sphere deployments early in the experiment with highly varied trajectories due to interactions of the various forcing factors that I've already mentioned. But for example, in the first deployment here, the westerly winds send this 4060, this drifter, all the way into the inner part of the fjord and grounds right here near the low river pretty rapidly. But the tracks of 460 on the 24th to the 27th show this oscillatory pattern, which is due to the daily change in the winds and tides that drive the drifter back and forth over most of the basin, and it eventually grounds up here at Gold Creek. Now, in contrast, let's see, I got this one. Contrast this drifter I-5480. It moved initially on the end of these diurnal winds. It moved inward, but then it was caught on this outward flow, this current at night, and it rapidly moved out of the fjord, down into the Narrows, into Valdez Arm, where it turned around and came back in the next day, and it ends up going all the way up here and milling around the Gold Creek and Mineral Creek area, and finally grounding at Gold Creek. Let's see. Okay, there's two more ice spears deployed on the 24th to the 27th, 9460 and 6350, and they show oscillatory patterns in their tracks as well, especially moving down to the southeast like one of the other drifters did, and then moving back. But whereas the 9460, it moved inward at first on those westerly winds, but then moved right back out overnight. It moves back to the north and is driven in again by the winds, but it turns right around and then grounds up here near Gold Creek. The other drifter also moved to the southeast, but when it returned, instead of continuing going back and forth in the fjord, it went north, and then the wind drove it all the way in where it grounded up here near the Valdez Glacier stream. So the microstars showed some similarities to the ice spears, but they're driven by near-surface currents only, and to some extent wave action. So the deployments in this panel show completely different trajectories. So Drifter 7, it moved inward during the same diurnal wind that drove the ice spear 460, and whereas number 1 moves outward on the same current on the north side that moved I-5480 overnight. But instead of continuing on out of the fjord, it stops and is just driven back the next day as the diurnal winds can start up again here. So in this next panel, the Drifter 7 here in red, it shows the same oscillatory pattern that the ice spears did after it first went down again to the southeast and then turned back on itself back to the northwest. The other drifters, especially for number 1, was released late in the day, and it ends up going straight out of the fjord and ending up going right down the Narrows. And this is kind of why I was thinking, Scott, that the chute, if it's putting out a flow, it could be going down the shoreline, and you're right, some of it could be moved back into the fjord, but then it's going to move back out possibly at night. So the other two drifters showing the oscillatory pattern, the last one here was 3. It went also to the southeast, but when it moves back, it stays up here in the north, moving back and forth. It's moved inward with the wind and then moves back out at night. Okay, so this is a panel showing 6 consecutive ADCP plots. And this is what I really want to show out of this plot is how much the structure of the flows change over time with the differences in these winds and the tides and the estuarine geostrophic driven flows. I'm going to focus on a couple of the patterns here in more detail. This first flood and ebb, and the second flood 2, ebb 2, and then ebb 2. So if we look at those, for flood 1, when the diurnal winds are just beginning to pick up, the flow in the outer basin shows a cyclonic counterclockwise turning out here with all this subsurface flow moving out on the north. And this is typically a feature for the latter part of the ebb tides. So in ebb 1, however, the winds are actually moving surface water in now. If we go back to this other plot, we can see that. This was the first plot on this flood 1, and then this next one here in the orange is right in the middle of those winds. So it's moving surface water in, and there appears to be a response barophoniccally out here in the fjord with these ebb currents accelerating, apparently to try to maintain the balance of the tide volume change as it's going down. Now on the next set, we have a different time period here, so let's go back to those. And those are done here in the middle of the night and in the early morning hours. So what's happening there, I believe is happening there, is now that the estuarine flow is moving out, it's forcing a subsurface inflow. And here on this beginning of the ebb tide, we see because of this, that the ebb currents are mostly being driven out. And I didn't mention this, but these are all the long channel velocities. So they're what's moving in and out of the fjord, not going across. But ultimately, this flow begins to slow down, and that subsurface flow abates, and so we no longer see that strong outward flow. And at the end of the ebb tide, that's where this cyclonic pattern starts to show up again. So here are the SVPs at 10 meters, and what do? When every one of these starts showing a cyclonic flow pattern, it just in different magnitudes. This first set, number 4, was put out, and it did a very quick turnaround, but it's moved to the north with that northward flow moving out along here, which seems to be a persistent flow according to the ADCP data. But once it gets to the outer fjord, something happens here that drives it to the south, and I am not sure what at 10 meters could be forcing, pushing water in against that to suddenly force it southward. The ice spheres do the same thing in some of these deployments, and I wonder if when you have a northeast wind, if there's a wind emanating from Chute Glacier that forces them across. We'll see that for the September deployments. But all the others do the same thing. They turn cyclonically, even in the inner basin. Here, number 8 also tries to turn cyclonically, but when it reaches this boundary, it turns back on itself and goes anticyclonically back to the south and out. The 40-meter drifter, I only released one in June, and it had very little motion. It slowly, but just gradually moved in for about 11 tide cycles. There's evidence of one period where it may have accelerated here, and that's when we have this fairly strong westerly wind moving in. And if it did, that is a subsurface baroclinic response. It's not a directly driven by the winds, because the wind momentum is really captured in the very upper layer. There's too much buoyancy in the water column for wind currents to get down that deep. And even if they did, the Ekman layer down would be very small. But it certainly could be moved in as a subsurface flow in response to the wind transport. That is actually something that has been seen in Puget Sound. It's a subtidal response of winds where you get different layers moving either in phase with the wind or out of phase. So this next panel is going to be a dispersion experiment in June that I performed from the 27th to the 29th. And it was done with triplets of ice spheres, microstars, and SVPs over these deployments here. So if we start with the ice spheres, we'll see that they moved in and then back up to the duck flats area and then stop. They disperse when they get back up into the duck flats area. So they're moved northward at first by what looks like a northerly wind until the westerly wind picks them up and moves them inward. Then at night, when the westerly wind relaxes and it blows from the northeast, they start to go back to the northwest, and then they end up here in the duck flats. Now, the microstars do a completely different pattern. As you can see, they move back to the south, then the southeast, and then they disperse along the southern shores. They move to the west. Now, the SVPs at the deeper depth do a completely different pattern. They do the cyclonic orbital pattern that was suggested in the ADCP data. So they're going to do these widening orbits until they finally hit this outer current in the north, and then they start moving out and dispersing outward. Now, the second deployment of the microstars was done a little bit farther out in the fjord, but it was also on one of those westerly winds. It has a different pattern than the first set of microstars. It's a lot like the first ice spheres. So it moved in with westerly winds, but then turned back to the northwest, just like those ice spheres did. But they didn't turn directly north like the ice spheres did going to the duck flats. Continued up into this area near Mineral Creek, and then turned back on itself. Now, I am not sure what caused that reversal exactly. Okay. So this is the characteristics of dispersion. And these first panels are the speeds of the drifters. And the second set of panels are going to be the dispersion characteristics based on the average distance from the center of mass, which is done mathematically to determine what the average is. It ends up, because the masses are the same, it's just the same as the average distance between the drifters to get that center, and then you just take the average distance to that center. And then the other measurements is the change in the size of the area, and then the rate that the area is changing to get you a dispersion in meters squared per second, which is essentially an eddy viscosity estimate. So if we go back and look at these speeds, you can see that the ice sphere deployment accelerated pretty quickly at first, and they don't disperse until they head up into the duck flats. And where we see the variance in these individual velocities, that's where most of the dispersion takes place. The same thing occurs with these microstars. They disperse some as they move southward, but when they go westward along the southern shore, that's where they have the main dispersion. So we can see here with the microstars, after 10 hours, that's where their dispersion increases. The ice spheres increased as they went up towards the duck flats, but then they were pretty evenly distributed after that.
What do you attribute the dispersion to? Is it like a bunch of water rushing in, or why would they?
Well, it's essentially most of the flows always have an element of turbulence to them in oceanographic flows. And it's a horizontal turbulence that would do this, but then it's the case here at Port Valdez. That turbulence may move the drifters apart, but then it also can bring them back together. So some of these rates go up and down. Back here, let me show you that. See, you look at this for these microstars here, where the rate goes up, it goes down, back and forth. So the turbulence has effects in different parts of the flow. But that's primarily what's going on here, and this is an estimate of what that turbulent viscosity coefficient would be. It's actually one of the hardest coefficients to get an estimate for in modeling, for looking at turbulent effects in flows. Okay.
Is that something I'd call like a tide rip, or?
Yeah.
Eddies.
Eddies.
Yeah, the tide
Like
rips.
lots of little eddies, and so each buoy is in a slightly different area, so it gets caught differently, and it moves them apart.
Yep, you've seen the small eddies in those tide rips. That's exactly what it can be at small scale. So the second set of microstars had a very similar speed profile as those ice spheres, because remember that they had a very similar trajectory track as they went in. The only difference is that there's a lag in the time that they moved. Now their dispersal maximizes right at the middle of their drift, right here, and that's when they're actually moving into the fjord from the west to the east, when the wind is having its effect. But then it drops off. So now look at the SVPs. Their average speed's low through the whole period. They show some cyclical ups and downs of the speed, but the average is only about 10 centimeters a second through the whole period. But their dispersion is out here at the end of the drift, where we see them after about 25 hours. We start to see them moving apart more, and that's on that northerly current. So there's going to be a little more turbulence associated in that northerly current at 10 meters. Okay, so this panel here, I'm going to talk a little bit about retention versus flushing. Again, it's based on this average along channel U velocity, and since the basin is oriented east and west, the U velocity itself is an along channel flow. So this is the flow that's actually moving the water out or pushing it back in, but not across the fjord. So in each of these here, we've got a positive side and a negative side. and the positive side represents the retention, and typically the values are going to be positive in all those, but occasionally I put some of these in retention even though they have very small negative net flows, and the reason was that, for example, in 460, remember, it just moved back and forth inside the fjord, and it never ever really exited. So even though the along channel velocity is slightly negative, it would have taken that flow 20 days to finally get out of the fjord. So I'm considering it retention. And it also, there's grounding. The G on here, that represents grounding. So I kind of consider that to be a retention by default once it strikes the shore. But anyway, so the maximum retention in June occurs in the surface layer. 93% of the time, these deployments, versus only 7% of the time for flushing. And the only real flushing was that one ice sphere that got sent out by the estuarine current at night, and then it came right back in here the next day and grounded. So with the microstars, we see a bit more flushing, but still the retention is much higher. It's at 81% versus 19%. And then with the SVPs, we see still more retention versus flushing. The 40 meter drifter obviously was 100% retention because it never did anything but stay inside the inner basin. So what does all this mean for areas that could be at risk for contamination? And so what I've got here, we have the winds during the survey period down here with the histogram of their directions over here. The oil, this is a schematic with a hypothetical idea of if the winds are blowing in from the west with this oil plume out and upward. So if it did make it into the middle of the fjord, then all these other areas would possibly be at risk, because that's what was shown by my drifter deployments.
So the hatcheries on the Solomon Gulch?
Yeah, and that's exactly where one of those ice sphere deployments grounded in there. That's where the red is here. All this hatched red and blue, that would be areas if the oil were to move, that southern shore is going to get affected just by default. But we see that because of the high retention in the ice spheres, that mainly it's the inner basin that gets hit, and then this one area at Gold Creek. But with the microstars, okay, there's high retention with them too, but because we had a bit more flushing, we see more of the North Shore and places here along Entrance Island and east of Anderson Bay that got hit. But this western shore I put out as a potential because there was a deployment that made it all the way down right along that shore, so it's possible that that could get hit as well. In the 10 meter, there was only two spots, but really just this one spot over here that may have been hit. So really it wasn't very much at 10 meters that viewed to be at risk, and nothing at 40 meters, obviously. So now start with the fall experiment. And the winds in this time show a transitional pattern between the summer westerly winds and northeasterly fall winds coming out of the interior. So here's the summer pattern here, and here, and here. And we had some of it during our survey as well. It just wasn't very intense. The magnitude's a lot lower. And that's partly because at the equinox, the solar angle is decreased by about 23 degrees, so we're just not getting as much heating going on. But the pattern of the winds are similar. But we're seeing these bigger patterns of northeast winds over a period of days as well, here at the beginning of the survey and at the end. And here the histogram shows those changes in the wind directions from the two predominant directions. So the temperature profiles, these were collected during the first flood tide on the 21st. And the interesting thing is that there's not a whole lot of variability except for the thickness of this mixed area here. And they do show some differences in the cold runoff within the this is the inner basin here from 17 to 14. This is mid basin, and this is the outer basin. So we can see the higher amount of cold fresh water coming in here. But there's also this thick, what appears to be a thermostat, and I believe that may have been a result of this really strong wind period earlier in the month. That preceded a period of heavy rainfall as well. So here are the salinity profiles over those same transects, and here's the interbasin, and we can see the differences in the freshness at the surface, but the rest of the profiles look fairly similar. There is some variance in this area that I'm calling a partial halostad, because it's a partially mixed area that goes along with that thermostat area. But there is some spatial variation in this halostat area, and I believe that that's responsible for some of these deeper geostrophic currents that I saw in the ADCP data. So looking at the temperature structure, same thing on the north side of the fjord along this transect, going from the inner basin to the outer basin, so that we're looking to the south through these transects. There's not a whole lot of variation to be seen in the temperature structure, except for changes in that thermostat. Except for, and you probably are not going to be able to see it in this plot, but if there's a thin cold layer from the fresh water that's up here, and that does change over time as we go into those northeast winds. And then when we get into the westerly pattern, E, it changes again, but you can't really see it in this plot very well. So what happens with the salinities, okay, here the fresh water is concentrated in the basin, and then when we get into the period of northeast winds, it starts to move out. And let's see, then we get to the period that runs C, with the north, we're right in the middle of the northeast winds. The fresh water, you can see that it's concentrated out here. So here we have, this is all northeast wind blowing for days, and that fresh water has been moved out to the middle of the fjord. I don't have the other measurements all the way out towards the chutes, Scott, so I can't say what happens when the winds change from the west eventually there. But on E, then we see the water it's moving back into the fjord. But there's also something else shown here in these data. And this deep density gradient has changes in it. It tilts, and that can definitely affect some of these geostrophic velocities deeper in the water column. See if we can see this as we go through. You can see the tilting. Okay, so the dynamic topography in September, we get something similar effects by the transport of the winds and the fresh water distribution. And so now the gradient in geopotential initially extends from the inner basin to the outer basin over these first two CTD runs. But you can notice that as we get into these northeast winds, there's evidence that the flow is moving that water out to the northwest. But in the next series here in C, when we're in the middle of those northeast winds, you can see the whole dynamic topography is shifted to the outer basin. Then back now here on E, after we get into the pattern where we start to get these westerlies with northeast at night, the whole pattern is shifted to the north again. Now, it's doubtful that these flows will all achieve geostrophic equilibrium, but there is evidence of that northwest dispersal here on run B. And run C may have been imbalanced longer, so the flows may have moved more to the southeast. See, if they're totally imbalanced with Coriolis, they're gonna flow in with a pressure gradient. Coriolis turns it until it is opposed by that pressure gradient. That's what we call a geostrophic flow. And it's going to want to move along the contours. But I doubt seriously that these flows are totally in equilibrium. When we start using that circulation model, we may be able to start answering some of those questions. But the interesting thing here on E is this zonal distribution in fresh water, because that definitely indicates an estuarine flow wanting to move out, but it probably turns to the southwest as shown here. So this is going to be the first set of surface trajectories. I'm going to show an animation on that. And it's these first three here going with the beginnings of these westerly winds that turn into northeast winds, and then number 4 is right in the middle of the northeast winds. So the first two sets we see that initial effect of the westerly, but then as soon as it turns northeast, these eye spheres just turn and they all head out. And that's what I was mentioning, Scott, about these turning down here to Entrance Island. Let me go back to this. Do this again. Because that looks to me like there could be a crosswind coming out of there to try to drive these drifters south. Now, I don't know. Dave, have you ever heard of any winds blowing out when it's coming down the June?
Yeah, you've got Middle Rock is there, so you've got the wind data on Middle Rock right there.
Yeah, but it could be coming right out of Chute.
Right.
Well. Yep,
right,
that's what I thought. So,
yeah.
so
that wind data is there for Chute winds, and you do see it quite often. You know, Potato Point or Valdez can be completely, east or westerlies, and Middle Rock, they'll be out of the northeast, right out of Chute.
Okay,
not strong.
Yeah. Yeah,
especially at night.
Wasn't sure if that was getting a real good measure of those crosswinds or not. I think I mentioned that in my report, though. You're right, because of those Potato Point winds. So these guys, both sets end up in the same location. And now, this set of eye spheres here was launched in the evening. They get driven right out with these northeast winds. And these guys can clear the Narrows, and they end up going all the way out into Prince William Sound, grounding here at Perry Island. Then C0600 refloats, makes its way southward through Night Island Pass, across Montague Strait. Then it's driven by a southerly wind northward all the way back up here to Green Island where it grounds. So Dave retrieved the first one, and when the Alpha went by at Perry Island, and then Rob Campbell and the New Wave retrieved the other one when they went out in one of their surveys.
That double back up to Green Island is just incredible.
Isn't it?
Never put a dollar on that.
But some of the old drifters actually went around Montague.
Yep.
Multiple times, going up
Montague Strait.
Up Montague Strait and turning around and going down the outside.
Yep. That was a summertime pattern when we released those, Scott. But yeah, I agree. It's just we were kind of hoping to see that drifter go on out of the pass and get out into the coastal current, but we were willing to sacrifice it for that reason. But okay, so here's some other trajectories of the eye spheres, and they're showing us an outward pattern on these lighter westerly winds, which is really interesting that they continue to go out. And it's this, the only thing that I could explain with this is that there's some holdback here with those winds, but the estuarine current must be pretty strong at this time in the north to be drawing these things out. And all of them went out. And then Dave Rendell and I went out and got all these down in the Valdez arm. So another set, though, as we get into where the westerly winds are stronger, now we start to see some cross-channel variations in the flows. They go to the southeast, both sets, but whereas these outward drifters come back to the north and then get caught in this northerly flow going out, the ones in the interbasin, they show a completely different pattern of dispersal. So one of them goes north up here, again, towards the Duck Flats area, the container terminal area here, and the other then goes right out to the northwest. And one thing that I think could be doing this, we observed the plume of fresh water coming out of the low river. It was coming out pretty heavily at this time, and it was dispersing. And I wonder if what we're seeing here is a dispersal on that plume. So you mentioned about turbulent flow. Well, there you go. If there's major turbulence moving these drifters apart in that particular case. So here are the microstars. I'm just going to play this through. This is all the deployments that we had during the entire survey, and you'll notice that almost all of them have this tendency to want to go out.
And that's all 1 meter depth?
That's at 1 meter, yep. Now that last one you notice started to turn back in. Now we're starting to see some variability, because this is where the winds are shifting to that westerly pattern, northeast winds at night, but you still see that northerly flow, and you still get these guys moving out, but now they're starting to get some southward motion to them as well. And I'm wondering if that has to do with that zonal gradient that I mentioned about the dynamic topography forcing fresh water more southward as it moves out. So these guys are moving southwest like I was thinking that dynamic topography was doing. So that's almost at the end. And then here's two more again. They're forced southward before they move due west. This one here ended up grounding. So I think that's the end of it. One more. Yeah, this is the last one, but all those last deployments then had a south component before moving out. Okay, let me just go to the next slide because, okay, this is a summary of all those deployments that I showed you all the way up to that last deployment where everything moves southward before going westward along the southern shore. So the main point is here that with the microstars, everything at 1 meter just had a tendency to want to move out of the fjord, except when the winds started to move into this other pattern. That's when we start to see more cross-channel variability. Okay, the ADCP currents, again, in the fall, we see these large structural changes over a 6 series of sequential sets of transects. And down here is the flows across the fjord in the very first bin, which is up here at 7 to 15 meters. So that indicates how the changes play out horizontally over the fjord. So for example, the inflowing currents on the south side on the flood tide, which continue during the ebb. Let me go back to this a second. So if this, we're going to look at these first two sets. The currents flowing in up here on this flood tide, and they continue on the ebb, and that's what creates this cyclonic circulation in the center of the fjord. And it was pretty well resolved in this particular set of ADCP transects. So this flow pattern continues over the next two tides, possibly as a response to the continuous downfjord winds. But the eddy changes into more of a convergence region here, you see, because this northerly outflow is still going and continues through both of these tides. And so that convergence then changes to where it's all flowing out here. Now what happens also here is we end up with some deep inflows at about 60 meters coming in during that ebb tide. It's possibly in response to all that strong flow in the upper water column going out. Now, farther along towards the end of the survey for the oceanography work on the 25th, we got another complete change in the structure. So what happens here is the upper 7 to 15 meter bin has very little current. So our transects are going outward this way. And as you see, as we go farther out, the cyclonic flow is evident in the subsurface water. That's these patterns here: outflow, inflow, and so forth. And it shows up almost all the way down to 47 meters. So that pattern continued right on through the next ebb tide, which is number 9, and I don't show that one. So now let's look at the SDP trajectories in deployments 1 and 2. And what happens with these guys is we start to see the cyclonic flow pattern that the ADCP data showed, particularly out there in the outer fjord. They also start moving in on a southerly current and outward on a northerly current. That same current that we were noticing moving out of the fjord up here is moving this set right here, number 5, out, but it precedes this number 6. It's interesting that it's lagged. So while these guys turn westward, this anticyclonic flow, number 5 lags behind the first one, number 5, and it takes a whole other day or so to get all the way out here to the outer basin. But it's consistently moving outward, no matter what the tides are doing or the winds. Now, some of the other patterns of flow, the cyclonic orbits were not viewed again until near the end of the surveys. But the northerly outflow and southerly inflow, and shown in the ADCP data, were definitely at work causing vorticity, and the two sets of the drifters that showed those reciprocating flows were 1 and 2. But after the period of downfjord winds, then the drifters exhibit mostly anticyclonic clockwise turning with gradual outflow, indicating flushing. So all of them just show this. You see some of these tidal effects on them. They move in and out, but they do gradually start turning anti-clockwise and move out along the southern side. These guys went back and forth here, but still the general trend is outward. This group here went in at first, so there was some separation, but they too often eventually turned south and then move outward. Now at 40 meters, they move relatively slow in comparison to the 10-meter buoys and remained in the water over long time periods. For example, the drift of number 2 here, which was released on deployment 4, it covers nearly 15 tide cycles from the 22nd to the 30th. Now, but these drifters also exhibited pretty wide cyclonic turns in the outer basin and smaller turns here in the inner basin. But there wasn't really much evidence of wind effects in this layer until possibly on the 29th, when that long period of northeast winds took place. That's when these drifters suddenly kicked out of this mode and moved along the north shore, and they ended up nearly grounding out here. And that this could be a subsurface effect of the transport by the winds.
That's amazing. That's what's that in 40 meters is
130
to 30 feet, yeah.
it's the wind had the effect of.
Well, it's not a direct effect. Remember I said that the direct effect, because the Ekman layer, it drops off exponentially as it goes down in depth with the direct wind momentum. So it's a response, baroclinic response to transport in the upper layer. And as I mentioned, Puget Sound shows this kind of effect where that upper layer is moving out with the winds directly. The subsurface layer will go out of phase, and a deeper layer will then be back in phase with the winds. So you get these reverse patterns.
I'm thinking fishing and blowing really hard southeast, and fish are going to be moving this end of the flats.
Yep. And down below the Ekman layer, it could be a reversal.
Wow.
So anyway, let's talk a little bit about the retention and flushing in September. And for the eye spears, we see a bit more flushing, but the retention in terms of time of the drifts is still favoring retention at 62 versus 38%. But there are some fairly strong net negative velocities. I put them up here in retention mainly because the drifters never exited the fjord. They ended up grounding. So what happens with the microstars? We see the effects of all the negative U velocities and all that flushing. So we end up with 85% flushing versus only 15% retention. And there's very little grounding. There's only a couple of deployments where these guys went aground. So in the SVB 10 meters, we see nearly equal amounts of retention and flushing, even though it's a very, very tiny net negative flow. That's so small, it really indicates that there's more retention, which according to the times of the drifts here, it's 55% versus 45. These three panels right down here are for the 40 meters of buoys. They're all flushing, but again, I've got a couple of questionables here when those two drifters went along the north shore and nearly grounded along the shore. So some of that water could have touched the side of the fjord over that area, but it would have continued flushing on out most likely.
Those are the deep moorings, the
Yeah.
dark ones?
Yeah,
They're 40 meters,
40 meters.
100% flushing?
They're all negative. Yeah, they all went out over time.
Yeah.
So they all ended up flushing. But like I said, along that north shore, some of those ended up possibly grounding, but still the water would have probably eventually continued to go out. So what does all this mean for the areas at risk? Okay, so here's our wind patterns over the survey. Here's the histogram of the wind directions. And if we have winds moving in both directions, then this plume of oil could move both ways. So I expect more of the southern side of the fjord to be impacted. And once the oil reaches mid-fjord, then we might see some of these other areas impacted. And it's interesting because the inner fjord area still shows some carryover from June. We still see some of these areas in the northeast side possibly at risk. Gold Creek's again at risk, but since we have some flushing going on, some of these other areas out here in the outer fjord may also be at risk. Now the microstars, because they flushed right on out, we don't see much in the way of areas with them, just up here in this one spot east of Mineral Creek. But the western shore, definitely, because of all that outward flushing, we saw dispersion and motion along that shore, so that's definitely at risk. The 10 meters, maybe up here at Mineral Creek, maybe down here towards Solomon Gulch, but not much. And then here is the 40 meter that there's two that end up coming out here and coming close to shore. Okay, so I'll finish up with the March experiment. And we started, as I mentioned, with the cold, dry winds moving in and flushing water out of the fjord. And here's the air temperatures through the whole period of March. And in blue are the air temperatures when we had the survey. So you can see we went from a pretty cold period with an increased trend in air temperatures to by the time we started. But there is a downward trend when we're doing the oceanographic survey, and then it comes back up again when we get into this period of snow. It's a bit warmer. And here's the snow equivalent in moisture right here. Oops. This thing is not responding very well to my movements. I don't know why it's doing this, but hang on. Yeah. All right, I'm not going to touch it. Just, come on. There, finally. Okay, so there's the wind pattern through the whole month, and we can see that the winds were very strong through the March. It was really high gusts up above 20 meters per second and even higher. Now they came down somewhat during our survey period, but in the initial part of our survey, we had a lot of strong winds. At first, we got this lull in the winds, and so that allowed us to get out and actually get some data collection done in the first day. But then we got stuck for a day until we could try to get out again on the lull of winds here and here. But we really didn't get very many surveys done. It was only like 5.5 runs with ADCP transects. And here are the vectors for the winds during the whole survey. So we started with this oscillating pattern of easterly, southeasterly to northeasterly, and then finally it went into a long period of northeast winds that were consistently from that direction. Then the winds abated and it got calm on the 29th. Then we started to pick up these real light winds from the west. At the very end of the survey, the west wind picked up for just a brief period of time. Okay, so the hydrography in March, it's very uniform. You can see by the CTD cast over here that in the outer basin here, we have very uniform temperatures and salinities. And in the inner basin, we start to see some fresh water, cold fresh water coming in. So there's the cold, and there it's fresh, but it's so small in salinity change. There's not a very huge density change. These are the 3 TS diagrams for these 3 casts, and you can see with the sigma T changes, it's very limited. And then by the end of the survey, it's all very mixed. So we really didn't have any density changes to drive any kind of geostrophic flows in the water column. Everything is really being driven primarily by the wind and the tide. So here are the ADCP currents, 2 sets of transects that were during those high winds. and we see some places here where there's a jet of flow. And this is the jet coming out of the low river right here and here. And that's turning to the northwest, and that's pretty much where our surface drifters ended up as well. So if we look at the drifters, two different stages of these winds, these are the eye spheres, and when the winds were blowing from the southeast, they rapidly moved to the shore up here and grounded. This other set also moved up, but we got a hold of them before they grounded. Now when the wind shifted to the northeast pattern, they at first moved directly out, but then they start to move to the southwest, and they end up grounding right down here in Anderson Bay. This is the first deployment of these guys, and they just go straight to the south. And this is the second deployment, which is in these winds right here, where it's moving them more down fjord, and then when the wind changes, it drives them ashore. Now what happens with the microstars, we get the same thing on these easterly winds, a motion to the northwest, but instead of grounding, they are moved on a current that's set up along this north shore by wind transport towards that shore. So what's probably happening is you're getting a transport setting up a sea surface elevation change, then it's trying to restore itself, and it creates a barotropic flow outward along that shore. Now, on the northeast winds, they still move in that direction, but you see some tidal changes going on here until they get caught on that current. Then at the very end of those winds, they start to move in.
How many tides was that last one?
Let's see. About 1, 2, 3, 4 to 5, something like that. So this whole period.
So it's still moving out on the tides.
Yes, because the tidal currents have a very minimal effect relative to the wind at this time of year. So the SVPs, they do the same thing under the southeasterly winds. They move out, they move along that barotropic current, moving out. They start to disperse when they get out to the outer fjord, though. But under these northeast winds, after getting to the northwest and moving out on that current, instead of moving southward, they start to disperse along the north shore and they ground. When we get to this light wind, they just turn in and ground. So this is what happens when we get into this period where at the very end of these northeast winds and we have all these lighter winds in the calm period. The first set of eye spheres under those winds do get moved to the southwest, but they don't ground for the whole time. They end up moving along the shore and dispersing. But when they're redeployed under this light wind, the whole system changes and they start moving in with tidal flows, and they start into this anticyclonic pattern. And then finally we start to get a bit of west wind here that starts moving them in with against this ebb tide, so they kind of move to the southeast. Now what happens with the microstars, this is the continuation of that deployment where they turn back in into the east. They start into this pattern of cyclonic orbits until they finally kick out of that and move to the south like this. So that's through all of these tides. So the tidal currents are probably having some effect out in here, but at this point, through this whole period of drift, it's these northeast winds. The second set of these that were launched right after these guys, they show the same pattern. Both all moving to the northwest, moving out with that current. Then when the winds abate, they start into this cyclonic pattern, and they too start trying to kick out of that pattern towards the end. Now the SVPs, when I redeploy them after they came to the outer fjord, when these winds are turning very light and from the west, they show no indication of wind. It's just turbulence. They start into this cyclonic orbiting. The outer ones are undergoing a very wide pattern, but then they turn out here to the southwest. So the 40-meter SVPs constantly moving out under all the winds and tides. It does look like there's some acceleration when we have ebb tides and some inhibition when you have flood tides. But during the southeast wind, it's continual motion moving out here. And then when we get into these northeast winds, they start to make a turn to the south. And as we get to the end of the southeast winds and into the period of low winds, they make a very wide cyclonic turn. And again, they turn to the southwest like some of the other drifters did. So let's look at the patterns of retention and flushing. Now, almost all the ice spheres were flushing, but if you considered all these groundings to be retentions by default, we'd have 100%. But the flushing still, in terms of the time period of the drifting, is still less than the retention because of this long period we're going in at an average inflow of 5.6 centimeters a second. So what happens with the microstars, they too are mostly flushing outward, but we have some retention going on with those cyclonic circulations during the period of low winds. The SDPs, they too are all mostly flushing out of the fjord. Let's see, the two 40-meter deployments are here in the gray and the brown, and this is one of the 10-meter deployments that was very lengthy. Then this one here is when they are doing their cyclonic orbits. And the question is whether they're flushing or going to be retained. That's questionable. So I don't know for sure if it's 100% flushing, but I put it at retention 10% because these guys did show that they were staying in the fjord. So now what happens with areas at high risk? This is the worst case scenario in March. Obviously, with winds going either direction, if they're blowing out of the fjord, then wind is going to move the oil outward, and this whole area out here is going to be at risk on the southern side. And when the winds turn back into the westerly pattern, even though it's light, they could move in with tide and wind and hit this inner basin as well. So we can see that potentially the surface contamination could be all the way across this northern area and all the way out in this southwest area here. And if it flushed all the way out of the fjord, then out here in the west could also be hit, particularly with the 1 meter flow. Now, I didn't get any drifters getting all the way out of the fjord because I kept retrieving them before they could make it out of the fjord altogether. But anyway, you can see that both sides of the fjord would be highly at risk. So if you were to put dispersants on the oil at this time of the year, you basically just send oil contamination at 0 to 1 meters all over the place in the outer fjord. Now suppose that the contamination occurred with oil moving slightly inward. Well, it might take a while for the oil to reach the inner basin areas so that you could possibly get some containment in then, but still, if it continued in under those winds, these areas could also be at risk too. So just in summary, the winds during the early summer and fall and late winter, we saw the patterns of the diurnal sea breezes with shifts to the northeast at night, the westerly winds with periods of stronger northeast winds in the fall. Late winters, we saw the reciprocating pattern of northeast and southeasterly and northeasterly winds with a long period of northeast winds and then a period of calm winds and light westerlies. The hydrography goes from very shallow stratification, the cold surface layer with the alpine and glacial runoff, so it's a very shallow halicline, to a deeper thermocline and halicline with a thick thermostat and a quasi-halostat in the fall extending all the way down to about 40 meters. Vertically mixed conditions in the fall with very minor TS gradients, and this mixes over time due to the winds. The geostrophic currents, well, we got patterns varying in terms of where the dynamic heights are highest in the outer basin or the inner basin, depending upon the wind transport of the fresh water. And the same thing happens in the fall, just with a different pattern of setup. We have this zonal pattern when the winds were blowing from the west, as opposed to moving the water all into the inner basin rapidly, as we did with the strong sea breezes. Late winter, there are negligible currents due to the vertically mixed conditions. The ADCP currents at less than 5 to 15 centimeters a second in June. They're concentrated in the upper water column, except during the period of weak winds. The flow structure becomes inverted due to the estuarine surface outflow. In the fall, the currents increased in strength to 5 to greater than 25 centimeters a second and are deeper in the water column. The cyclonic flow becomes more prominent below 15 meters late in the oceanographic survey. Now, in the winter, the flows were barotropic, and they produce a jet of flow during the period of high winds out to the west and northwest. The drifters, okay, so in the summer we got these oscillatory motions with one of the drifters going outward at night, going into Valdez Arm, and then returning back with a westerly wind and a flood tide, and ultimately grounding up here at Gold Creek. In the fall, we get oscillatory, 1 meter. We still also get these oscillatory motions, but with some downfloor flow beyond the mouth and into the narrows. So in the fall, the downfloor flows increase with some drifters entering PWS, and others show some wider cross flow motions with frequent grounding. In the 1 meter, that's all downfjord flows with a limited reversing back into the fjord and some cross-channel variation when we get into the lighter winds. In late winter, we went from strong southeast winds with all flows in the northwest with the iospheres to under the calm winds. We start to get, we had this one pointed to this northwest when the winds were still blowing from the northeast, but under the light winds we got this varied structure due to just turbulence in the fjord. In 1 meter, we saw the same outflow to the northwest and outward along the northern shore, but then when the winds relaxed, then we started to get the turbulent effects, and we see these cyclonic orbitals. So I'm going to go straight to conclusions here. And so the circulation in the port's forced by the combination of tides and geostrophic flows that are highly moderated by winds. These vary seasonally, and in the summer and fall patterns cause continual changes in the mass field, thus constantly affect the estuarine conditions within the fjord. The deeper density field also drives baroclinic flows, particularly in the fall. These flows are also moderated by surface transport by the winds and possibly also to sea surface adjustments after the winds abate. The seasonal circulation patterns affect the amounts of retention and flushing, with strong diurnal westerly winds causing retention in the summer, but the shifting to downfjord winds in the fall, along with marked estuarine surface and subsurface conditions, resulted in greater flushing, particularly at 1 meter. In late winter, all depths exhibit flushing during strong east winds, but changes into retention when the winds relax. Areas at risk also vary seasonally, but there is some overlap in the summer and fall for areas in the inner basin. Sensitive sites expand in the outer fjord in the fall due to the stronger flushing, but in late winter, the worst case scenario is in terms of the surface and 1 meter contamination, which would occur along most of the fjord except the inner basin. So I just want to acknowledge that the funding and outreach came from the RCAC, and Jeremy Robita helped with the setup of the pre-deployment meetings. He helped me with editing the manuscript, and I'd like to thank the crew, the MV Aucklet, Dave and Annette Janka, and then Dave Reynolds, who was the captain of the Vixen, and Brad Reynolds, who was a crewman in the winter, and then especially my technician, Kirsty Jurica, who helped me in all the surveys. And I'd like especially to thank Dave Janka for all the great photos that he took to document all the surveys.
And Jeremy Robina commented that he was watching online.
Okay, great. So anyway, thanks, and I'll take any questions now.
So not much signal from the tide.
Well, you know, it's a barotropic tidal current's pretty weak because the whole basin's so wide and deep.
Yeah.
But the tide can appear to be enhanced when you have those when it's interact with those baroclinic flows. And no doubt there's some points where it looks as if the tidal currents are being accelerated, but it's a response to transports in the other layers, changing the volume.
But you don't see the drifters with a real distinct tidal-driven pattern.
No. They'll occasionally see them. They'll be inhibited by, say, if they're trying to move out on a flood, and then they'll accelerate some on an ebb. So there are subtle responses in there, but not strong. So the main thing is the geostrophic estuarine currents and the moderated by the winds. So those two are the two major factors really driving the variability in the port. So you can see it's a pretty complex circulation setup, and it's interesting how much turbulence can come and go in the system. But also, there's quite a bit of differences in where oil may impact, particularly the surface in 1 meter, depending upon the season and what the winds are going to do.
You mentioned models. Are we going to put this into a moving model?
Well, that's the idea. Yeah, we have a ROMS model set up, which is a regional ocean model. It's been set up by Yi Chow for Prince William Sound, and he wants to take the domain down to the level of Port Valdez and then use all my data to help ground truth, and we'll validate that model. So that too will help answer some of the hypotheses that I've derived and I've been talking about through this presentation, just from the observations. That will help verify whether some of these things are really driving or not in the flows. So,
And you're saying at depth too, that there's kind of a stagnant area?
Down in the deep flows, the very deep flows, let's say down below 100 meters, they typically don't have real strong currents there. They were at about 5 centimeters a second or less for the most part.
5 meters or 5 centimeters?
Centimeters.
I
Yeah,
say
so,
5 meters, man. Okay, good, centimeters.
sorry, I didn't mean to say meters.
boy,
If I did, it's centimeters.
I can't walk that. I can't move any. So, but down deep, it's just a long.
Yeah, it's very slow. Yeah, most of your motion's up in the very upper water column. But as you saw in the fall, it did deepen because of the mixing of fresh water down into the water column up there. That halostat was a real interesting phenomenon because it just went from that really shallow halocline to suddenly that mixed area down there, down from about 20 to 40 meters.
Wow. Okay. So, are you going to give this presentation to the RCAC board, or?
I don't think so. I think